Back to the afternoon session. And so we have a couple of talks this afternoon. And the first one is given by Michael Flatté, and his title is Magnon Enhanced Quantum Technologies. So,
All right, thank you very much. All right, so it's a pleasure to tell you about some of this work. I have done some of it at University of Iowa, some at Eindhoven University. None of it at the small quantum sensing startup that I'm associated with, which is QuantCAD LLC here. But if any of you have any questions about what it's like to be closely involved with a small quantum startup in the US, let me know. I'd be happy to talk about it individually. So I've put up here a few examples of some topics we've looked at in quantum technology, including photon polarization entanglement, some spin properties, some molecular features, and then some that I'll talk about here today. I am particularly calling out some of my collaborators in this because two of them are here, Dennis Candido and Thardier Puel. So they have contributed essentially to this work. Okay, so I will also mention that some of the slides that you'll see here, if you saw the tutorial on Monday, there's a little bit of overlap, not so much. And I also took out the slides relating to our little adventure and the with the car and Carlos on Saturday. But if there are questions at the end, I'd be happy to pull up the other presentation and show those pictures again. So this is one that I mentioned before because it kind of describes how I think about the types of things I'm doing. I'm interested in reversible control of matter with external fields. And very often when you are trying to do this, you're working with electronic systems, and the electronic systems are in some kind of incoherent and uncorrelated thermal equilibrium, and then you manipulate those properties of its surroundings in order to do some kind of information manipulation or transfer. So the classic example of this is a two-level system. I've got a region with two locations, perhaps one is a 0 and one is a 1. You can think of this as a transistor where the channel is charged or is not charged, so it's related to the gate. And there's certain criteria you have to worry about for this. You worry about the separation between the two locations, because if they're too close together, the electron can tunnel through. And you worry about the height, because if, interesting, let's try that. You worry about the height, because if the height is too low, then at room temperature you can be thermally activated over the barrier, and then you lose your information. And so this gives you criteria for switching. And this is, there's a lot of development in the semiconductor field about exactly how to talk about this, but it's not totally crazy to think about estimating the amount of energy cost for doing manipulation is related to lowering that barrier, moving your electron over from one side to the other, and then raising it back up again. So it largely consists of charging and decharging a capacitor, which is what's giving you the potential in the middle. And so then when you're looking to make faster and faster semiconductor electronic devices, VLSI, then you can try to reduce the energy by reducing the number of electrons that's switched. You reach a certain limit when you get to a very small number of electrons, because you could miscount, and then you get fluctuations in your voltage on your downstream gates, which is bad. And so you get some kind of fundamental limit related to the individual electron and then the number of them. So what I like to work on are ways around this, either using correlation. So if you tie all the electrons together, then you can switch them with an energy that's still a lot larger than kT, but the individual energy for each electron is less than kT, and you don't suffer from these issues of counting the number of electrons, the shot noise kinds of issues. And this is the area of switching magnets and ferroelectrics, even mechanical switches. And then the other area is coherence, where you don't worry about being in thermal equilibrium. You're going to remain outside of thermal equilibrium for the entire time of your calculation. And then you can work with small energies that are less than kT that are applied to each electron and even get to the regime of single-spin coherent systems. Okay, and often there are relationships between these two that offer new opportunities. All right, so let's take a look at quantum technologies and ask, why are superconducting qubits so challenging to work with? And in fact, the list we could have here is very long, but I'm going to focus on a few of them. You might ask, is the issue that I'm working with a superconductor and therefore I have to be at low temperature? And the answer to this is that that's actually irrelevant. At the temperatures you're working with, the things are already going to be superconducting. The relevant temperature you're working with is related to the occupation of the microwave photon with thermal occupation. Microwave photon at 5 gigahertz. And so that's, sort of around 200 millikelvin, and you need to be a lot less than 200 millikelvin in order to be able to do good operations on this. And so that's also what I showed in another context on Monday, which is our LC circuit here. It's a nonlinear LC circuit because you want to separate the energy from 1 and 2 from the energy from 0 to 1. That's required to give you a well-defined qubit in this situation. And that nonlinearity is given to you by the superconducting system. And so the superconducting electronic device is this really tiny thing. Here's my L, my wire, and you can see that's a little blow up over here. And there are the two Josephson junctions that are giving you that nonlinearity that is essential for quantum computing to detune the 1 to 2 transition from the 0 to 1. As I mentioned also on Monday, this is a very large object. This is 300 microns, and that's because you need that in order to get a good coherent microwave photon. And as is often observed, this already looks huge, but in fact this is one of the smaller early transmon qubits. Now they are often 10 times bigger, because the bigger you make it, the longer the coherence time is going to be. It just makes everything, though, really slow, because the nonlinearities also get smaller, which means the detuning that you can work with is smaller, which means that everything takes a long amount of time. So, the superconducting technology is in a really tight box. And the basic problem is that these things are all big. So you might say, well, let's do spins. Let's work with these systems. They're lots of fun. And you certainly can do that. The fundamental operation for doing for doing quantum computation is to do 2-qubit operations. And so you can think about that in the context of entangling 2 qubits. And the usual way you do that is with some toy Heisenberg Hamiltonian like this here. And here I have my 0, my 1, has my up and my down, and I can have triplet and singlet. And you see that my singlet is split off as a nicely entangled state there. And as a result, if I start with this in a product state, say up-down, that would be the sum of the singlet and the T0, and then I let the system evolve for a period of time such that the phase changes by pi, then I go from singlet plus T0 to singlet minus T0, or minus that, and that corresponds to this here minus that, so that's down up, and so that's 1, 0. So that's swap, or actually, I guess technically it's I swap. And if you want to do exclusive OR, which is the fundamental operation for quantum computation, that's related to the swap to the 1/2. Swap to the 1/2 being just doing this for pi over 2 instead of for pi, because you do it twice. You get swap to the 1/2 squared gives you swap. Because we're very creative in how we name things in quantum computing. Okay, so here's the issue, just using one example. It's not a great example, but we've calculated the exchange coupling between NV centers, which are very nice qubits, as a function of distance, and compared it with the dipole. And so these values that you look at, I mean, they're minuscule. This is this here is a log scale. So as I separate these things by distance, over short distances, the exchange dominates, but as soon as I'm out at about 2 nanometers separation, the exchange interaction is 10 micro EV. And if I go out even further, if I go to 10 nanometers, the exchange interaction is minuscule, and it's lower than the dipole interaction because that falls off with a power law. And we're down here essentially we're already going to be in the nano EV. So that's really, really, really slow. So the basic issue is that your transmons are big, your spin qubits are small, and if you know how to use these beautiful integration tools that we have, that ASML and others provide for designing various systems, the integration scale that you want is really going to be in that 1 to 10 micron scale. So how do you get there? How do you do things on the 1 to 10 micron scale? Okay, and so this is where I at least think that coherent quantum magnetics can be helpful. Here are some of the advantages of coherent excitations of a magnet that I like. It's really nice that you have an object that has a Q equals 0 excitation. That Cattell mode is very nice. You don't need to fit an oscillation with a finite wavelength into a certain box. The lowest excitation of the box is Q equals 0. There's always that uniform mode. You can even, because the spin wave velocity is so low compared to light, you can even confine these in micron scale structures if they are non-uniform excitations. And you really have very strong direct coupling to microwave fields. And I'm just going to say, there was a lot of work on quantum spintronics, which you sort of have to redefine, because as soon as you have a conducting material that is not a superconductor, all of your experimentalist friends stop listening if it's quantum, because the charge noise just absolutely kills you. And so in these systems, many of them are insulating, and so you don't have the charge noise. You've quenched it. Now, that's a generalization, and in fact, a lot of what we work on now is trying to figure out how charge noise sneaks its way into these systems that you don't like. Disadvantages, we're working with often very different material systems, may not have been characterized for these kinds of features, particularly at low temperatures, because magnets are typically used at room temperature, and quantum, because you're looking at these gigahertz excitations, it's all low temperature. So there was a lot of debate about what the line width is for YIG at low temperatures, and identification of new dissipation mechanisms below 300 millikelvin, because nobody cared about 300 millikelvin before quantum for YIG. Now, the quality factors are good. I mean, we love these numbers, 10 to the minus 4, maybe 10 to the minus 5. They're good, but they are terrible compared to many other quantum coherent systems. And so, as a qubit, it's generally pretty terrible, pretty bad. Quality factors are bad, the nonlinearities are actually quite low. So, in addition, you have these inhomogeneous broadening effects that are often poorly understood. So this is all the things you fight at. So the question is, what would you do with this? What's the advantage that you want to take? What kind of technology are you going to focus on? And so from my point of view, looking at this, the targets are gates and transduction. You want to use the magnons to help you with gates. You want to use the magnons to help you with transduction. You don't want it to store the information for any period of time, because it just isn't competitive. Okay, so here are 4 examples of things, and I'm going to attempt to talk about all 4 of them to some degree, because they each illustrate some aspect of how, when you try to do a different kind of quantum device, your criteria and your materials and your configuration change from one to the other. Fortunately, Tharnier talked about the one in the lower right already earlier this week, so if I run out of time, sorry Tharnier, that's the one that's going to get less time for discussion. All right, so let's begin with this first one in the upper left. And so this is a proposal that we had for entangling NV centers using YIG. This work is done with Dennis Candido. And I'll begin by kind of reminding you of a few things for the NV center. So the NV center in Diamond, it's a beautiful spin 1 object with a great toy Hamiltonian. It is a spectacular room temperature quantum sensor for some things. And again, as somebody who has some involvement with a quantum sensing startup, I can tell you a lot of things about what it's good for and what it's bad for. It is a very niche thing. There are actually a lot of other quantum sensors that are potentially much more commercially practical, but it does hit the sweet spot of lots of things that particularly condensed matter physicists care about. So that's part of the reason why it tends to get a lot of attention. All right, so our Hamiltonian has a magnetic field term, it's got a zero field splitting term, and another one, so this is the axial one, this D term, and then there's an off-axis one, which is the E term, which often comes in with electric field or other kinds of effects. So this is some work from quite some time ago where they used the NV to identify the direction and magnitude of the magnetic field. Because what you're seeing here is the resonance frequency, and there are always two of them, right? Because it's a spin 1 object, so it's going to have two resonance frequencies. Well, sort of plus the third, but and as a function of direction and magnitude, you get this kind of feature. Direction because it knows about the axial term, and magnitude because that's the size of the splitting beating against it. So it's a beautiful vector magnetometer with a variety of techniques that have been used to improve it. Okay, the reason I want to mention this is that we're going to try to couple that NV. That's the fruit fly that I'm using. I want to study the magnetic system and just use a very ordinary spin system to be coupled from one to the other. And this was motivated by this nice work from Daniel Loss's group, which has magnetic regions connected by a one-dimensional spin chain, and these magnetic regions are imagined to couple to spins underneath. And this has many features, but it's perhaps a little less practical than the approach where you're using a material like yttrium iron garnet here with kind of real numbers for what you can achieve in terms of positioning NVs. All right, so let's look at this in some detail. This work is in PRX Quantum 4 years ago. We are interested in a YIG bar that is sitting next to the two nitrogen vacancy centers. These are individually initializable, so that's what's indicated over here. And we're imagining that they're separated by about a micron, because that's the key. We want to be able to couple, want to be able to entangle two NVs that are a micron apart, which we're not going to be able to do with dipole, not going to be able to do with exchange. And so this is being proposed as done with a virtual excitation. So the NV transition is this dashed line over here. Here's the frequency. And the dispersion of this bar with a magnetic field pointing along the long axis of the bar looks like this. This is the characteristic feature with a backwards volume mode over here. So the group velocity is opposite to the phase velocity initially. And then you have this exchange-dominated region over here, but the key that we care about is that you have this huge buildup of the density of states sitting at an energy that is higher than the NV, so it cannot make a real excitation in the bar, but it can create virtual excitations that can then be absorbed by the other NVs. So you can have a mutual spin flip through this process. Okay, and then we can calculate, and by we I mean Dennis, calculated the field for these NVs that are sitting a certain distance that's reasonable away. They cannot be too close to the YIG, because if the NVs are too close to the surface of diamond, then their spin coherence times gets terrible, and we're relying on relatively coherent nitrogen vacancy centers for this to work. And then you can calculate the coupling strength as a result of this. And you get a relatively strong coupling, but it improves even more if instead of having a infinite bar, you take a finite size bar, say 3 microns long, and you position the two NVs some roughly, 1.5 microns away. So these plots here are showing the entangling rates between the two NVs as it processes from singlet to triplet and back again, so they're becoming entangled. And the rate of this is quite quick. It's about a megahertz. And the gate to decoherence ratio that's calculated for this is almost 1,000. So these are very promising numbers for realistic, scalable 2-qubit gates. Okay, and then you can look at the properties in more detail. I am a theorist, so I am guaranteed to be showing you some equations. So here's how these are done. This is the density matrix dynamics calculated with Lindblad equations over here. And then various quantities are calculated as a function of time, including the CH-SH violation, negativity, and fidelity. And so that's being shown over here for both real and virtual excitation, and we've done this also as a function of temperature. So as you might expect, if you're at very low temperature, the real excitation is going to win because you don't have any fluctuations in thermal occupation. If you're at higher temperature, then the virtual excitation is going to tend to do better than the real excitation. Okay, and now, this is based on this CH-SH violation calculation. And this was recognized a couple of years ago with a Nobel Prize based on this work in 1969. So I always like to show for the junior people around that if you do something important and you want to be recognized for it, it's very important to live very long. Eat your vegetables. Make sure you eat the fruit, not the dulce de leche cake. But in any case, if you look at this over here, why did they give it to Clauser? Well, he is the first author, but H here, he's dead. And S here is also dead, and H left the field, decades ago. So really, they only had the one person that they could give it to. So they didn't have to worry about this. Only 3 people can get it for this particular part. Okay, now what about experimental sides of things? Well, doing this measurement is not easy. I hope you don't feel that that's a kind of a strange statement coming from a theorist, but I really do respect the experimental work that needs to be done in order to try to do these things. It's really, really hard. So this work here came out last year. This is in collaboration with David Oshalom's group at Chicago. And so the initial trick is not to actually do it with 2 NVs, but just to do it with a single NV, where it's a self-interaction measurement. So instead of exciting the magnon and then having it interact with the second one, it's actually exciting the magnon and then coming back and interacting with the same one. So that is very similar to a relaxometry kind of measurement. And if you look at the behavior of this as you cross the NV excitation with the magnon excitation, you see a dramatic increase in the relaxation rate. And so this is modeled essentially without fitting parameters. It's a nice direct connection between the two, which tells us that we have a very high quality calculation of the coupling strength. So that's very reliable. So this peak here occurs just when the magnetic field causes these two to cross. And if you change the magnetic field, you'll also see a change in where that crossing is. This is the parallel magnetic field. And so you can see that that tracks with it as you proceed. Okay, so that's entangling spin gates. For the spin, again, we were using the fruit fly NV, but we used yttrium iron garnet because it had this nice strong coupling and this confinement and these long coherence times for the magnons. I'm now going to talk about spin-magnon transduction over here. It's a completely different material that we've decided to focus on, completely different configuration with magnetic field out of plane. It's a disk, it's not a bar. And part of the question is why? And it's not just because we know people who grow these things, it's because this particular material is very well suited for this property. All right, transduction. Transduction from a kind of basic point of view is exceptionally similar to the entangling gates we had before, because now instead of these spins that are split in this way, what we're splitting is the occupancy of the Magnon mode with the spin of the NV, but it's the same kinds of combinations. And in this case, essentially swap is a kind of transduction, although there are ways that you can do more interesting types of conditional effects. Okay, so here is this work on magnonic coupling of spin qubits. We're using this magical material, or a vanadium tetracyanoethylene, which is an organic ferromagnet with a very low saturation magnetization, which is not great, but it also has an exceptionally low damping. It has a line width, a loss line width, essentially an alpha parameter of 3 times 10 to the minus 5 in thin film form, which is actually better than most YIG that you might find. And probably it's because the saturation magnetization is less. All right, and then we look at transducing between Magnon modes and spin flips. So here's the energy diagram for the NV. So here's the transition from 0 to -1, transition from 0 to +1. And then at some point that transition is going to cross the magnons. And now you can see why it's really important to have a very low loss material, because this is not a thick line here. This is in fact several lines. And when you blow up the scale, you can see that this is the separation. And if you're picking a particular line in here, you want to interact with just that Magnon mode, not any other Magnon mode. Otherwise, you're going to have, you're going to lose your fidelity. You won't be transferring your spin information to a clear Magnon occupancy. And we want a disk that's relatively big, and so these lines are close together. We want a disk that's a micron in scale, because that allows us to do transduction to the Magnon occupancy and then maybe transduce back to another NV in that kind of process. The nice thing is that these modes that I'm showing here are actually chiral modes, so they move around the disk like this. We are going to focus on high angular momentum modes, and the reason for that is we want the fringe field to be as big as possible, which means we want to confine the mode towards the edge of the disk. So the mode towards the edge of the disk will give us a larger magnetization associated with a single magnon at the edge, but that's also going to have kind of as a compensating challenge that the decay of that fringe field will be shallower, because the decay is related to the wavelength of the magnon. Okay, and then we calculate the cooperativity, which is related to that NV Magnon coupling, which for reasonable parameters is about 10 kilohertz. And then we use experimental NV coherence times and Magnon decay rates, and we get a cooperativity that can exceed 1. I will mention that this configuration with a magnetic field out of plane is required because that's how we get these modes that are confined to the edge. If the magnetic field is out of plane, it means we have to tell our experimentalist friends to buy 111 oriented electronic grade diamond, which is even more expensive, if you can actually find it, than 100 oriented electronic grade diamond. But because of the way things are in the world, and that academic groups will typically pay less to element 6 for the diamond than, say, other entities, it can be extremely challenging to actually get this material. So it's been very nice to see the establishment of academically driven foundries to grow good quality diamond in various places around the world. I can't even remember. Okay, good question. Well, so I'm hearing a few things, but you're saying it's the Magnon occupation of the mode. So that's a temperature-dependent quantity. So in principle, you cool down sufficiently low, and that's 1, which you want. So we're going to assume that we're at 1. All right, so here's the calculation of the cooperativity sort of as a function of position from this. And now we, as theorists, even expand further in our respect for the experimental community because of how difficult this is. I'm showing slices that are 80 nanometers below the surface of this disk, and also slices that are on the edge over here. The green here is the disk that's involved. And what we're looking for is cooperativities that are actually not just 1, but well in excess of 1, because that's where you want to be. And so you can see that this is possible to find, but then I'm adding this other feature, this little white box here, because when you put the NVs into, essentially the nitrogen, into the diamond, you have a certain precision of the implantation. And that white box is indicating the precision of implantation at the time of this particular paper. And you want it to be sufficiently below the surface that you don't have a problem of coupling. But it does tell you that you should be able to get cooperativities well in excess of 10 for this kind of configuration. And we think that it could be considerably better with maybe other types of spin systems. Again, we're using NVs as our fruit fly. And I'll just mention, as I did on Monday, that there's been some work that's quite similar to this from the experimental group in Würzburg, where they looked at the vortex structure in permalloy, and they used silicon carbide as the location for their spin centers. And they're looking at silicon vacancies in the silicon carbide, which are really nice spin 3/2 objects that they can manipulate. And this should look familiar from some of the other plots I showed earlier for our systems. All right, now to the lower left over here, strong coupling between photons and magnons. We've heard a lot about this already in this workshop. I'll just mention where we got into this game. Our thinking was really motivated by this beautiful work that came out more than 20 years ago now about strong coupling of in the electric dipole situation. So this is strong coupling of a single quantum dot exciton and the cavity mode in a microcavity. So this is simultaneous work from Forshell Group. There was Dennis Deppy's work, which I think is this down here as well. And the coupling is relatively strong, but this is a really, really hard thing to achieve. Now it becomes much more routine. But the thing that we observed in this case was that the tuning was non-ideal. So the way they're tuning it here is they're changing the temperature from 30 Kelvin down to 5 Kelvin. And in the process, the semiconductor band gap is going to change. It's going to increase, whereas the cavity mode doesn't change at all. And so you see this anti-crossing over here, which gives you that 80 micro EV splitting. And so we thought, well, maybe there's a way that we can do something like this that's more conducive to tuning, and that was based on magnetic field tuning, which, while not the easiest thing in the world, is definitely a lot easier than temperature tuning, a lot more sort of better way to do some kind of tuning. And so these proposals over here were realized in the work of Hans Hubel, who I'm happy to hear is going to be here next week, where he demonstrated this nice anti-crossing. And this is the work by Hong Tang that I think we've also seen earlier this week. All right, so our interest in collaborating on the experimental side with people trying to do this was to try to get to a lithographically convenient system. And so I'll remind you of our transmon over here, where we have our LC circuit. And so here again is a superconducting LC circuit here. There's no Josephson junction in the line, but what's been done is that a magnetic material has been deposited on top of that. And that magnetic material is this vanadium tetracyanoethylene. And the reason for that is it's a lot easier to deposit that than something like YIG, which destroys the superconducting thing. You'd have to put the superconducting thing on top of it versus the other way. There's been a lot of revolution in the development of this organic ferrimagnet, mainly the ability to encapsulate it so it doesn't decay very rapidly with time. This is using encapsulation procedures that are very similar to how you encapsulate the OLEDs that are in the phone or in televisions, so that you can use organic devices for, kind of people-relevant timescales of years rather than research-relevant timescales of days. All right, so here's the resonance of that superconducting cavity, and here's the strong coupling demonstration. So this is the strong coupling between the magnon and the resonator. These are an assortment of various lines in here that appear to be connected to higher order excitations. They have narrower line widths than the main one, which is something kind of characteristic of the non-uniform modes of the system. And that's a subject of additional debate and considerations. This appeared last year, and then of course there are a lot of other recent experimental demonstrations in various settings of this kind of strong coupling between the microwave photon and the magnon excitation. I think I had, no, okay. So you may or may not recognize your contribution up there then, although Axel is not here today. All right, so there is some time to talk about microwave to optical transduction. And I do want to, again, kind of emphasize the strengths of using magnons here. It's always used as some kind of mediating feature, so it's mediating the interaction between the NVs. Here it is the destination of a piece of quantum information, but you can think about this more as a bus that's taking that information around and maybe exchanging it between NVs rather than as a final destination, because the coherence times may not be so long in that material. Now over here, we're going to look at one of the main challenges for long distance quantum interaction, which is how do you get your quantum communications, which is optical fiber-based and kilometers in scale, to interact with your superconducting quantum computers. And so you need to be able to transduce quantum information from the microwave to the optical regime. And so we started this some almost 10 years ago now, looking at direct effects inside a material like yttrium iron garnet. So this is just using the fact that the index of refraction of the magnetic insulator, yttrium iron garnet, is going to be different depending on the direction of the magnetization. And as you excite a magnon, then you end up with a change in that, which gives you this coupling. This is also at the simultaneous with work by Sylvia and Florian, with slightly different foci of interest. Essentially using this kind of nonlinearity, we were able to show that you can in principle move information around. Our motivation for looking at this was really coming from Dan Stamper-Kern's work on cold atoms, where he was doing very similar things in that system. And you can pretty quickly see that you can mimic many of the features of the optomechanical systems in optospintronic systems. You can get electromagnetically induced transparency. We can get the Purcell effect depending on the relative order of the optical damping, the magnon line width, and the coupling. So you're typically working in a situation where your coupling is in between the two. If your line width is very small for your Magnon compared to the optics, then you get your EIT. If you're in the other regime, then you get the Purcell effect. And this was motivated by work to try to understand how to use Magnons as a kind of quantum memory that basically failed because their coherence times are really not long enough to be competitive. Quantum memory is maybe not the thing you want to do. But if you're looking at microwave to optical transduction, you have a major problem that you need to solve, which is it's always good to try to address a problem that people have been struggling with for 10 years, because then the experimentalists might actually listen to the theorists. If they think they still have good ideas, they're usually listening to their ideas rather than yours. So this was kind of fun. So rare earth spin mediated transduction basically works this way. You have a rare earth atom, typically erbium. Erbium is the favorite because it has that 1.55 micron optical transition that connects with fiber optic lines. And the reason for that's pretty straightforward. That's because all of the light for those lines in the classical regime is generated by erbium lasers. And so you have this really nice level structure over here, this lambda structure, where you have two ground state spin states of the erbium. This is typically the Z1 up and down. And then you have an excited state, which is typically the Y1 state. And there's a non-zero matrix element that goes for between the ground state pseudospin down and this upper state, and the ground state pseudospin up in this upper state. So you have a nice connection. And then what you do is you drive this transition with a coherent light field, which means that if you put in, since this is a nonlinear optical effect, if you put in a microwave photon, you're going to get out an optical photon. If you put in an optical photon, in principle, you get out a microwave photon because you have a connection between the two. And so this is an example. This is from Andre Ferron's group about 5 years ago, showing that they're able to get a transduced signal that they have very helpfully normalized over here. Any ideas why they've normalized the signal? Because the efficiency is absolutely terrible. It's 10 to the minus 5. And the basic reason for this is that the coupling of the spin of that erbium to the microwave is absolutely terrible. So that's a huge challenge. Essentially, you have an atom, and it's got a little magnetic moment, and then you have this huge extended microwave field that you're trying to couple to, and so it's 1 over the volume of the 5 gigahertz microwave field. So really terrible. And there are lots of ways that you can try to get around this, and this is an area of very intense and very expensive effort to try to improve this, because there's no great way to do this, to solve this problem. All right, so our idea, Tharnay's idea and mine, is to use magnons to amplify this effect. And kind of the way we connect one to the other is you start with this and you say, well, the big problem is the interaction of the spin with a microwave field. That's just terrible. So let's make the system more complicated, because as theorists, it's always the best thing to make it more complicated. We're going to introduce another level so that instead of the microwave coupling directly to the erbium, it's going to couple to the magnon. We know that's a strong effect. We know that that's possible, not really a problem. And then, because the magnon is right next to the erbium and the magnon is very localized, it will couple much more strongly to the erbium spin than the microwave field would couple directly. So this process, even though it's a higher order process, is in principle a much stronger effect than just the direct coupling between the microwave and this. And you also have this advantage that you don't really need to worry about the modal overlap, because the coupling between the microwave cavity and the Magnon is so strong anyway that the real modal overlap you care about is in that nonlinear mediating element, which is the erbium atom. And so your magnet can be of micron scale, which is also the optical scale, and that helps. And again, in this particular situation, you should be thinking about the erbium as an ensemble of erbium that are, sort of distributed evenly throughout the mode, that are separated far enough apart that they don't talk to each other directly through dipole exchange. And this is one of the cases where actually the very rapid fall off of the coupling between two spins helps you, because you can get them relatively close. You can get a certain density that's sufficient to actually derive this effect. All right, so then we can calculate the various quantities that are relevant for this. And I would say that this is actually one of the fun places where interacting with an experimentalist can be very helpful, because the kind of metric that you might think of as a theorist that is useful may or may not actually be the kind of metric that they care about. And it's almost the case that one of the key things that we do here is define what is the metric, because before this, the actual metric that's involved is basically fixed, because all of the spin-based approaches always had this exact same issue of coupling between the spin. The moments were all approximately the same between the spin and the microwave. So this is essentially a measure of the rate of the process relative to the pump. Because of course, if you're a theorist, you can say, well, I can always crank up the coherent pump that's acting on that lambda system, and then my rate's going to be faster. So that's not fair. I need to normalize it by the rates. That's what this S over omega is. And then this is the case without the magnons. And you can see the strength is relatively weak by comparison with the case with the magnons. And this is also kind of the, down here we're trying to tell the story of what you care about, because of course you can always find a transduction rate that's going to be much greater than 1 if you go too close to the line. And so you need to put in the line width. You need to make sure that you don't get so close that you're there. That's what's being shown here. The gray region is a region where you're going to start having real excitations. You're going to lose your virtual process. And so if your S over omega is about 1 over here, over in this situation, you can get easily a factor of 1,000 greater, which means, depending on how you look at it, that you're doing your transduction 1,000 times faster, so you have a 1,000 times bigger bandwidth. Or if you're fighting with your loss, that means that your fidelity is going to be bigger as well. I think I'm not going to talk about this one. This is just looking at some variations of parameters and how they affect the various quantities as you think about what materials you might choose. I'm not going to show that, but I am going to, I won't show this either. But I'll come back to this aspect of what materials we care about in a couple of slides, because I think I have just 2 more slides. So my earlier promise to do 2 hours, I don't know. Well, we'll see. Okay, so I wanted to show you this because it's fun. When you work with an organic ferrimagnet, you have opportunities you may not have with other materials. Vanadium tetracyanoethylene has very large spaces. It's very porous, which means you can put other molecules inside of it. This is something that people like Jeff Long at Berkeley have been working on for a long period of time, starting with things like hydrogen storage and then carbon dioxide, trapping, when we actually cared about that, and into these things. So what he was interested in looking at was whether you could put other kinds of things into this material. And that's kind of important because when you look at the line width of this, it's probably dominated by the presence of some kind of unintentional molecule that's sitting in one of these pores. When we do a model, and by we I mean again Dennis, when we do a model of this line width as a function of temperature, you essentially come to the realization you probably have some undesirable molecule in about 10% of the pores over here, which is absolutely terrible. It's an incredibly dirty material, but the line width is still spectacular. Offers promise for the future. Okay, but it turns out that you can actually load into these systems all sorts of molecules. You can load in hydrogen, nitrogen, oxygen, carbon dioxide, ethane, ethylene. They all go in, and you can get about 50% load in there, which means that it should be possible, without damaging the magnetic properties of the material, to put spins at various places within the material. Okay, so summary slide here. What are the material and device opportunities for quantum magnonics? I mean, this is really a problem of coherent dynamics. The magnetic excitations are low-loss, strong coupling means of coupling things. They just don't have good enough coherence times to really be the qubits themselves. So that pushes you towards hybrid systems. It pushes you towards virtual excitations, and I'm learning about other places where they may be constructive, where that line width is not necessarily so bad. Now, we find cooperativities in transduction much greater than 1. Gate-to-decoherence ratio is very large. What materials would you think about exploring? Well, if you want to do transduction, you need a really low damping. So 5 times 10 to the minus 5 is probably the minimum, because that tells you have 3 gigahertz, you have 100 kilohertz line width, which, sort of about where you'd need to be. And, you are probably operating with magnetizations the order of 100 Oersted temperatures that, I would say you would want your magnetization to be at least 100 Oersted and your Curie temperature to be at least 100 millikelvin. This is an area that is completely unexplored, because basically when people looked at magnetic materials, if it didn't have room temperature magnetism, pretty much it went in the trash. So are we going to find materials with very narrow line widths, much narrower than these? Almost certainly, but nobody has been looking for them because the temperatures that are relevant for quantum are so different. Now, the criteria for quantum memory are just really terrifying. I mean, probably for the worst quantum memory, you're going to need a damping of about 10 to the minus 7, 300 hertz line width, because otherwise, why is anybody going to look at your system when they have 1 millisecond coherence times in other settings for memory? And so for that, you also don't need a large magnetization. You still need, a Curie temperature that's, probably greater than 100 millikelvin, and you're probably going to be working with a large anisotropy. But this is really a regime where there's a lot of potential materials work for people to do. I think there are a lot of exotic rare earth materials that are going to be out there. They're going to have very interesting and promising properties. So with that, I'm just going to put up the acknowledgements. I'll mention again in this list of people, Tharnia and Dennis, who are here, and thanks for your attention. Happy to answer any questions.
Right. Thank you very much for the very interesting talk, and we're on time. So any questions?
For the transduction with the spin ensemble, so I think one issue, at least for the kind of quantum memory with spin ensembles, is this inhomogeneous broadening, right?
So I'm still trying to narrow down which system you're talking about.
The spin ensemble coupled to Magnons, coupled to microwave.
So the last thing with the microwave to optical transduction,
Yes.
the rare earth-based spin system? Yeah.
And is this also an issue for the transduction, or you are okay with having a distribution of frequencies?
That depends on the detuning. So in these systems, it's actually transduction is much less this is much less of an issue for transduction than it is for quantum memory. So in quantum memory, you really care about this quite a bit. In quantum transduction, they work typically with materials that have much worse inhomogeneous line widths in a sense, because they just can detune away. So what they do is they take a material that may have a certain intrinsic inhomogeneous line width, and then they dope it to the point where the overlap is going to start to be comparable to that, and that's sort of their doping density. That's why they use yttrium orthovanadate for it. Yttrium orthovanadate doesn't have a great line width. It's got nuclear spins. The vanadium is right there, and it's giving you a width. So they would never use yttrium orthovanadate for quantum memory, but they can use it for transduction because the criteria are relatively modest. Now, if you want to do quantum memory, then you do yttrium orthosilicate or something like that, where you don't have the vanadium nuclear spins that give you trouble. So again, we picked a good system where it's much less sensitive to these issues.
For the self-interaction part,
Yeah.
together with David Auscherloom's group, is this equivalent to just a Lamb shift, or is it some real dumping
This
of
was the
energy?
real coupling. So it was not.
It was a bit quick for me. So the evidence of this shift was
So
what?
so
What
what
did
it
you-
shows, what we were showing is the peaked value of the relaxation. So it's a real excitation into the
It's
magnon.
being
So
dumped in. Okay. So
yeah.
it's,
So it's
like the
essentially
real
it's
part of
it's
that. There should also be a Lamb shift, though. Do you see any evidence of a shift in the frequency of the NV due to the
no,
presence of the
and
magnons?
that
Okay.
really comes down to the issue that the magnon is it escapes very quickly.
Okay.
So this is a relatively bulk-like piece of yig,
Yeah.
and the distance is very large, which it's 400 nanometers away for the NV to that. That is basically a problem.
Okay.
But the main thing is that the magnon doesn't stick around long enough to give you the shift, but
Okay.
it will give you the decay.
Okay,
So
I
it's
see. Thank you.
essentially very similar to relaxometry in this sense.
Okay, thanks.
Yeah, that's this one.
Can I, so I think Bill asked the question about the dog bone experiment.
The dog bone, yeah.
So what is the difficulty there? And actually, why is
Okay,
this
I
thing
mean-
that you measure just some kind of self-interaction? What is this useful for? Because the whole point of the dog bone is that you're making two
So the dog bone is a
spin-torque.
totally.
Yeah.
Oh, yeah. Okay. So
But that's still hard to measure, you said, right?
no. Well, we're being recorded, right? Okay. So often it's really useful to get motivated by a picture that might not be completely realistic, and so certain things that are maybe not considered but would be very important in a practical sense, you just forget about because you just want to understand how it works. And so that's how I look at this paper, right? This is a large magnetization, maybe 1 billion spins. And here we have one spin. And so the picture in this paper is that as that one spin is moving around, it is dragging around this 10 to the 9 spins. Now, I usually think that if I have 10 to the 9 spins, it will drag around one spin. And so if I think about the relative amount of dissipation, essentially I would expect that this is just going to lock to that up there. And that's going to be not what I want. And then, I also have this one-dimensional spin chain over here, which is good to sort of image mentally how things are going to behave, but it's not really a practical realization. So, for this, what we want to do is sit down and do something that doesn't get you laughed out of the room with an experimentalist.
You said that this is still hard to do, right? The
The- oh.
experiment in David's group now. Yeah.
Well, yes, but he didn't laugh me out of his lab. He, did the first step, and I think they're going to try other things later on. At least I hope they will. But, they didn't try this, right? because you look at it and you know it's not going to work. It's a motivating picture of how things could work. And so in that sense, it's useful, even though it's not a fully developed proposal with real numbers. So it's extremely valuable and
Yeah.
and motivating work, but it's not how you want to do it, in my opinion.
We have time for one more question. Yeah.
So since you mentioned about real numbers, I noticed on the cooperativity of the NV with the Magnon that work with Dennis, I noticed on the G you had 10 kilohertz in there,
Yes.
and it's how should I see that 10 kilohertz? It sounds a
That-
large coupling. How can
yes.
we expect to achieve this number?
Oh, so that took a lot of optimization in the sense that you're taking a 1 micron scale region and you're reducing the modal volume even more by pushing the excitation all the way out to the edge. You're then putting your NV near the edge and close to the surface, not so close that it loses its coherence due to surface noise, but as close to the surface as you can get away with in at that time current experimental regime, which was 30 nanometers. But yeah, I mean that's not an unreasonable number.
Okay, so no more questions. Okay, let's thank Michael again.